ABBC plus QCA, that is equal to 10,000 joule. That is a basic summation of all heats from ABBC and CA. This doesn't mean that the engine is 100% efficient. Here also whatever heat is transferred, that is equal to work done. But then also it doesn't mean that the engine is 100% efficient. All heat is not transferred to the work. Now PMM of first kind. What is PMM? That is perpetual motion machine. And first kind, let we see one PPT regarding this PMM of first kind.
Machine of first kind. In this session, we will discuss the concept of PMM1. The perpetual motion machine of the first kind is a fictitious machine. It is a concept used for understanding complex intricacies of thermodynamics. PMM1 is assumed to produce continuous work output without absorbing any kind of energy. Real-world machines are different from PMM1 because they require continuous supply of energy to perform work. Consider the case of a petrol engine. When we start the engine, the fuel mixture in the combustion cylinder gets ignited due to the spark and the cycle starts. The engine keeps running as long as the fuel is supplied. During its operation, the engine performs the work of rotating the shaft. As soon as we stop the supply of fuel, then the engine stops working. This behavior follows the first law of thermodynamics, which says you require continuous supply of energy to perform continuous work. As you can observe, the PMM1 indeed violates the first law of thermodynamics. Therefore, it is impossible to construct the PMM1. In this session, we discuss the concept of PMM1.
Hence, we studied that it is impossible to construct the PMM of first kind. Now, based on this, another example. A system undergoes the cyclic process A, B, C, D and E. The values of Q, W and delta U for the individual processes are as follows. Fill in the blanks, means find out whichever is not mentioned in this table. Process AB, Q, delta U and W. For AB, Q is unknown, U, delta U and W are given to us. Similarly, for all the processes, some entities are given, remaining we have to find out. So for that, how to solve this problem? Let me think about the solution. This table is given to us. First, for process AB, let me use the equation of first law of thermodynamics. Q is equal to delta U plus W. Q is unknown to us, dash. Delta U is equal to minus 60 kilojoule, that is reduction in internal energy, plus W, that is plus 40. So minus 60 plus 40 is equal to minus 20 kilojoule. Negative sign shows that heat is rejected from the process A to B. So let me fill up this blank. QAB is equal to minus 20 kilojoule. Now second process BC. Process BC, put the equation delta U is equal to the same equation. Put delta U is equal to Q minus W. This one, delta U is unknown to us. So delta U, Q is equal to 50, it is given. And W is negative, minus 60. So Q minus W means 50 minus 60. Double negative makes it positive. So 50 plus 60, 110 kilojoule. As it's a positive, it means that delta U increases. So internal energy increases from B to C, or UC is higher than UB, that is 110 kilojoule. So let me put that answer in this table, plus 110 kilojoule. Then process C2D, this process. W is unknown, so W is equal to Q minus delta U. Q is known to us, that is 60, and delta U is known to us, that is 70. So 60 minus 70, that is minus 10 kilojoule, and as W is negative, it means what? It means that work is done on the system. Work is not done by the system, it is on the system. The work is consumed by the system, hence W is negative. Let me fill up this gap, that is minus 10. Now last process DE. For process DE, two entities are unknown to us, QDE and delta U DE. Only W is known to us. So what should we do? We cannot use this equation directly because two unknown are there in this equation. So for that, think about the solution of this DE process. Yes, let me come from the basics. Sigma delta U for the cycle is equal to 0. So change in internal energy for entire cycle is equal to 0 because it is a closed cycle. So find out delta U for cyclic, then find out delta U DE, and after finding delta U DE, from first law we can find out Q DE. So let me find out. Cyclic delta U is equal to delta U AB plus delta U BC plus delta U CD plus delta U DE is equal to 0. Right? Put the values of all entities, minus 60 plus 110 plus 70 plus delta U CD is equal to 0. So delta U CD is equal to minus 120 kilojoule. The basic summation of this gives us delta U is equal to minus 120 kilojoule. So put the values, delta U is equal to minus 120 kilojoule. Now think about this entity Q. So from first law of thermodynamics, QDE is equal to delta U DE plus WDE, right? Delta U and W is known to us, that so 120 plus 90 minus 120 plus 90, so minus 30 kilojoule. So delta DE QDE is equal to minus 30 kilojoule, and negative sign shows that heat is rejected during process DE, and so we have found out all 5 entities of this table. Now next problem, based on first law of thermodynamics, the data is given like this. A cycle consists of 4 processes and heat transfer during process where plus 47 kilojoule, minus 81 kilojoule, minus 13 kilojoule and plus 41 kilojoule. Compute net work done of the cycle. Here suppose this is the system and cycle consists of 4 processes, and in first process heat transfer is positive, that is 47 kilojoule. 81 is negative, so it goes outside the system. Then third is minus 13, so it goes outside the system, minus 13, and 41 is positive, so it goes inside the system. So these are the 4 heat transfer. Whatever are positive, that is added to the system, whatever are negative, that is rejected from the system, and you have to find out net work done for this system. This is the data. Now think about the solution. According to first law, integration of cyclic delta Q is equal to integration of dW. So integration of dW is equal to basic summation of all this, plus 47 minus 81 minus 13 plus 41 all Q, that is equal to 47 plus 41, that is 88, 81 plus 13, that is 94, and cyclic integration shows that delta W is equal to minus 6 kilojoule, and hence minus sign indicates that the work is done on the system, or this system will not produce any work, it will consume the work of 6 kilojoule, and that is the solution of this problem. The next example, a certain quantity of air undergoes a change of state in such a way that 510 kilojoule of heat is transferred to the system. For this change of state, work produced is 210 kilojoule. Calculate the change in its internal energy. Assume that the process is non-flow process. So for that, let me think about the solution. W is given plus what 210 kilojoule. This is the system. This is the work done by the system, 210 kilojoule. Q is positive, that means heat is added to the system, 510 kilojoule. And what is delta U? Change in internal energy. This is the given data, and these are according to first law. Q is equal to W plus delta U. Put the values in this equation. Delta U is equal to 300 kilojoule. It's a positive. It means that the internal energy of the system increases. Now change in internal energy, delta U is equal to 300 kilojoule. That is the answer of that problem. Next problem, in a compression process, 60 kilojoule of mechanical work is supplied to 12 kilogram of working substance. The heat rejected to the cooling jacket is 40 kilojoule. Calculate the change in specific energy. So first, W is equal to minus 60 kilojoule. Work is done on the system. This is the system. Mass is equal to 12 kilogram. W is equal to 60 kilojoule. Q is equal to minus 40. That means heat is rejected. Q is equal to minus 40. And delta U, that we have to find out. So for this, according to first law, Q is equal to W plus delta U. Put the values. Q is equal to minus 40. W is equal to 60 plus delta U. So delta U is equal to plus 20 kilojoule. That is first answer. Then change in specific internal energy, that is equal to delta U upon mass, that is 20 upon 12. That comes out to be equal to 1.67 kilojoule per kilogram. That is change in specific internal energy. Now the basics of first law of thermodynamics.
Interesting about thermo, just kind of come in threes. I think we just like threes out of it. So let's just get started into it. So we have the first law. First law, I like to call it as you can't win. Basically what this says is that there's the change in energy of a system, whatever system it happens to be, some gas, whatever, is equal to the amount of heat added plus the amount of work done. So if you do work on a system, then that can increase the energy. We've talked about this before in the last unit on energy. It was called the work energy theorem, right? You can do work to increase or decrease the energy of a system. So what this is saying is that the total energy, and we're going to call this the internal energy, is equal to the amount of heat, and this is the change in energy is equal to the amount of heat given to the system plus the amount of work done on the system. Now work is something interesting where in this scenario we can actually have work to be positive or negative. Okay, positive or negative. A positive work is when you're doing work on a system where you increase the energy there. Okay, the work done by a system would actually decrease the amount of energy. You're expending energy to do work. So work can either be positive or negative. You can have a positive change in energy or a negative change in energy. The same thing can be said about heat. Okay, heat can either be taken from the system or given to the system. So in reality, both of these can either be positive or negative, and depending on those changes, you end up with a positive or negative change in energy. But what the bottom line is for that right there is that right down here, it says you can't get more out than what you put in. So the amount of energy that you get, the amount of change in energy that you get from a system can only equal the amount of heat you put in plus the amount of work you put in. You're never going to get any more than what you put into the system out of it. So let's say you do work on it and you give heat to the system, so you've inputted some energy. Well, if you have a capability of getting that energy back out, you're not going to get more out than what you put in. Okay, and that is law number one. This is really just a restatement of conservation of energy. It's just a restatement of conservation of energy. That's all the first law is. Okay. Just remind you that you can pause the video if you need time to copy this down if you're taking notes, or if I'm just going too fast, you can always rewind it and take a look at what I said again. So let's move on. So this is law number 2. Law number 2 I like to call is you can't break even. So what it says, no process is possible whose sole result is the complete conversion of heat from a hot reservoir into mechanical work. Okay, bottom line is you cannot attain 100% efficiency. So in the last slide, we saw that delta U is equal to the amount of heat you put in plus the amount of work that comes out of it. Okay. Now what the second law says is that not only can you not get more, but this equality is actually not even equality. You can't get as much out as what you even put in. Okay, let's say you do some work on the system and you add some heat into the system. If you're expecting to get anything out, don't expect to get everything that you put into it out of it. There's no way that you can get 100% efficiency. Okay, how this might look is in something known as a heat engine. And a heat engine says, okay, you have a reservoir that's called the heat source, something that's at a high temperature. You have something called a heat sink, which is a low temperature. And in between those two things, you put an engine, something, and we'll talk about some examples of what a heat engine might look like. Okay, and what the heat engine does is it takes heat from the high temperature area, the heat source, and it does something with it. You might be able to get some of the work out, and then whatever can't be converted into work gets thrown back into the heat sink. You can think about this as being the waste. Okay, this is waste heat. All right, so QH, theoretically, if you had a 100% efficient engine, QH would equal W, where all of the heat coming in, being energy, could be converted into work. The problem with it is that the second law says that can't happen. You're always going to have heat lost to, say, the environment or some other heat sink that is going to affect your efficiency. So the equation that we give to this is saying, okay, QH is going to be equal to QC plus W. Okay, really this again is just a conservation of energy type statement, but it's just telling you that QH is not going to equal W. There's always going to be some value